When you think about where to have a picnic, a type of place that might come to mind is a riverbank. Beautiful spot, serene, with just enough motion over the water to keep your eyes' attention. But really, is it that serene and calm? To a hydrologist or geologist, there's a lot going on underneath the surface of the water. There's swirling eddies. There's a frictional battle between the sides and bottom of the riverbed and the water. So that serene environment is not so serene. In an earlier video, we talked about weathering processes that break down rocks. And that's really not the end of the story. What happens to those byproducts of weathering? Well, they eventually get carried away by air, by water, and by ice. That's the focus of this video. We're talking about the transport process of those byproducts of weathering to other areas, in particular by rivers. So erosion is the physical removal and transport of the byproducts of weathering by various agents such as water, wind, and ice. In most environments, water is the most ubiquitous erosional agent. Yes, it somewhat depends on the climate of the area, but in most areas of the world, water moves the greatest amount of material from where it weathers to areas of lower elevation. Keep in mind, though, this process is ongoing, meaning it happens a tiny bit every day, but the bulk of what we think of as erosion by rivers happens when a river floods. This is really when the molding and transporting activity of a river is concentrated. And also keep in mind that as we alter the course of rivers, they don't flood as much. And we've been changing their sedimentation patterns. We're changing where sediment is picked up, how much sediment is picked up, and where it gets deposited. So we're changing the whole river system by our desire to protect the structures we often build on floodplains. So what drives this erosion? Well, really elevation. The higher the elevation, the faster erosion occurs. In a nutshell, mountains erode faster than lowlands. And you can deduce this from this map of worldwide erosion rates. The highest erosion rates are concentrated around the Himalaya Mountains and eastern China. And if you notice, Africa and Siberia have some of the lowest erosion rates. And when you zoom in on North America, the highest rates are in the Colorado River Basin. So if streams are the most important agent of erosion, then it makes sense that stream valleys are the most common landforms on the continent. They can take on a few different forms depending on the underlying geology, but the processes that form them are the same, flowing water. So I want to start with dispelling a common misconception is that erosion is the same thing as mass wasting. The driver is what makes them different processes. Erosion requires mobile agents such as wind, water, and ice, and the sediment gets transported by the movement of these agents. Note, gravity is not the main driver here. Mass wasting is quite different in the sense that the transfer of rock and soil downslope is due to gravity. So gravity is the key factor in mass wasting, and the movement of material does not require a mobile agent. Often water accompanies it, but that's not what is driving it. So when you see landslides listed as an erosional agent, that's incorrect. So it's best to really look at them differently, and that's how we're going to treat them. They kind of do the same thing, but they serve to flatten the Earth's surface by moving material from the higher elevation to the lower areas. But the cause of this mechanism that's responsible for moving the material is different. Erosion removes the byproducts of weathering. And if you recall from weathering, there's two main byproducts. One is the solid particles, the sand grains, the silt, or the clay. And additionally, there are the dissolved ions that are in water. So erosion removes both of these types of byproducts of weathering. Now getting to the solid particles that are a product of weathering, sedimentologists use a classification scheme to describe the size of the particles. It has nothing to do with what the particles are made out of, but there's a size breakdown. And most importantly are the sand grains, which are from 1/16 to 2 millimeters in size, and those are visible. You can actually see the sand grains. Anything smaller than that are either silt or clay, and anything larger than that is considered gravel, and gravel can be broken down into granules, pebbles, colloids, or boulder. There are three main components to moving a particle by wind or water. The first is entrainment, which just means picking up the particle. And it takes more energy to entrain a particle than it does to keep it aloft in the air or in the water. The second part is transport. That's keeping the particle aloft, and this happens in a number of different ways, which we'll talk about in a minute. And then once the energy of that medium decreases, the sediment gets deposited or it settles out. And this can happen when maybe a channel will broaden or when the velocity of the air or water reduces. The maximum size of a particle that a stream is capable of transporting is termed its competence, and it's strongly related to the velocity that the water is flowing. So when a particle gets deposited depends on two things. One, the size of that particle that's being moved and the energy level of that transporting medium. In general, high energy mediums like wind and water, when they have high velocities, can carry larger particles. When the wind dies down or the water slows down, the particles settle out. So particle size and shape can really tell you about the depositional history or the depositional environment of where the sediments accumulate. Gravels, for example, greater than 2 millimeters, are found in really high energy environments, such as mountain streams, some really high energy beaches. Sands, on the other hand, are found in kind of an intermediate environment, such as most beaches and maybe lower velocity river deposits. Clays are found in really quiet environment like lakes or in the deeper part of the ocean when there's not high velocity currents going on. And in addition to the size of the particle, the shape of the particle will tell you a little bit about how far it has been transported. Rocks or sediment that are very angular are considered immature and indicate that they have not traveled very far from where they weathered. More round particles are considered more mature sediment, and they indicate a more distal transport from when the grains weathered. And just a couple words about vocabulary. When we talk about river sediment, we call it alluvium, and that's basically the material that's deposited by a stream or river. And all these processes we've been talking about are called fluvial processes, and this is any process related to rivers. So a river really has two jobs. It's transport water out of the drainage basin, which we'll talk about in a minute, and then transport sediment that's delivered to the river. And that's a function of climate, drainage, vegetation, topography, and a lot of other things. So how is the work accomplished by these streams? So more specifically, rivers weather the grains that are brought to the riverbed by dissolution and abrasion. So they dissolve parts of the sediment. They can round the particles by collisions. The riverbed gets eroded by scouring of the water and the sediment that's in the river, transports the sediment from one place to another, and then eventually these rivers lay down the sediment. That's called deposition. So that calm river that you're gazing at really has a lot going on. It has many jobs to do. So a stream accomplishes all of these. However, one or more of these processes may dominate at different parts of the stream, whether erosion is happening or deposition, and that depends on the shape of the basin, the climate, and a lot of other factors. For example, deposition prevails where streams widen and flow across a wide open plain and become an alluvial fan. And dissolution may dominate where a tropical stream flows over limestone. So within a basin, these processes will vary both spatially and temporally. So exactly how does a river transport the byproducts of weathering? Fluvial transport is a process by which a river carries its load, and a load varies in size from really large angular boulders in the upper part of a river to suspended fine sediment in the lower part of the river. So load mainly comes from weathered materials that's rolled down the hillside onto the riverbed. However, it also carries sediment eroded from the bed and the banks of the river. So river transports material in 4 different ways. The first is dissolved load, which are minerals that are dissolved in the water and carried along in solution. And this typically occurs in areas that are where the underlying rock is limestone or chalk. And this is also how salts are removed from rocks and then deposited in the ocean. The next is suspended load, and this is the largest load of most rivers. Surprisingly, it's the fine, lighter materials such as silt and clay. These particles swirl along with the water without settling out. The particles are so light that they stay in suspension very easily. And this is the sediment that makes the water brown in certain rivers. And then the other part of the sediment load is considered bed load, and these are the larger particles such as sand and pebbles and cobbles that either bounce or roll along the stream floor. And that this is accomplished by two different ways: saltation, which is when small pebbles and stones are bounced along the riverbed, sometimes in suspension, sometimes hitting the bottom of the riverbed, or by traction, which is when large boulders and rocks are kind of rolled or dragged along the riverbed. So collectively, these four processes make up the load of the river. So mountain streams that come from high elevation and are very steep or have a high gradient erode and carry large bed load. So if you notice, a lot of mountain streams are very clear. That's because it's mostly bed load, not so much suspended load. On the other hand, at lower elevations and very slower moving rivers had a high suspended load and that really dark chocolatey color, such as the Colorado River. So when hydrologists talk about how steep a river is, they use the word gradient. And this just refers to how many feet or meters a river drops in elevation over a given distance. So units are usually feet per mile or meters per kilometer. Obviously, rivers with higher gradients have more energy and would therefore transport larger particles and sediments. Sediment found in riverbeds of these high gradient rivers are distinctly different from the sediment found in rivers that have lower gradients. It's indicative of the energy of that particular part of the river system. So the upper part of the river system near its headwaters, sometimes called its source, that has a steeper slope and higher velocity. And the lower part of a river system that empties into an ocean or a lake is known as the mouth, and that would have a lower gradient and lower velocity, and so finer grain size. So the gradient of a river changes significantly over its course. Let's turn our focus for a moment into exploring exactly how rivers erode. Streams and rivers cut through landscape because they possess potential energy due to their elevation above sea level. As they approach sea level, they have less potential energy and less erosive power, and at some point erosion ceases at sea level. Two types of erosion happen at different stages along rivers. At the upper part, usually in mountainous areas, vertical downward erosion occurs, which deepens the riverbed. This is mostly hydraulic action of the water and the sediment mixed with the water. So it's the energy that's left over after overcoming friction that leads to deepening of the channel and creating a really nice V-shaped riverbed. Further down the reaches at lower elevation, rivers erode by lateral or sideways erosion, and this serves to widen the riverbed, creating meanders. And this happens at lower elevations. But let's go backward for a minute and talk about how rivers actually form. So when it rains, water takes two very different paths as part of the hydrologic cycle. If the surface is permeable, such as in a forest or soil or grass, the water will soak into the ground to become part of groundwater. This is called infiltration. But on slopes that are very steep, or if the surface is impermeable, the water will either pond or flow downhill. As the ground becomes more and more saturated due to rain, this portion increases. The water that flows over the surface of the land then is called overland flow. And this is really that makes up the bulk of the water that's found in rivers. Although some of it gets added directly by rain and some groundwater may flow into rivers, the bulk is from overland flow. As a stream flows downhill, it merges with other streams, eventually creating a channel. When this happens, the smaller of the two merging streams is known as a tributary. Many tributaries will collect and dump into a larger or a trunk stream. So it's this branching network of streams that's known as the drainage system or the drainage network, and it collects water from a broad area, and that area is called a drainage basin or a catchment or watershed. They all mean the same thing. It's the area that drains into a major river. And this drainage basin is bound by a topographic ridge or a topographic high, and that's called the drainage divide. So precipitation that falls on different sides of the drainage divide will enter a totally different drainage system. So if you look at a map of North America and its drainage divides, you'll see that the land surface is divided very unequally. So the continental divide is what separates drainage networks that terminate either into the Pacific or the Atlantic. So most of the water that falls in the U.S. drains into the Gulf of Mexico and then joins the Atlantic. So it's only a small portion of North America that drains into the Pacific Ocean. Before we examine how rivers erode, we've got to take a look at the velocity patterns within a river, because that has a lot to do with where erosion happens and where sedimentation happens. And remember, erosion happens where velocities are greatest, and sedimentation or deposition happens when velocities are the lowest. Determining the average velocity of a river is really difficult because it varies over the course of a river. The upper part may have a very different velocity than the lower part, and even different parts of the river have different velocities. And the name of the game with the velocity of the water is friction. So any part of the river that is in contact with the river bed, so the sides and the bottom, there's a lot of friction and the water slows down. So in general, the fastest part of the river flow is up at the upper part of the river on the surface and in the center, which is away from the sides, and there's very little friction there. So a lot of rivers curve and they meander, and in a curved channel, the fastest part of the stream is towards the outside of the bend, not completely at the edge, but the outside part of that bend, somewhat like a car swerves to an outer edge of a curve on a twisty road. So we would expect erosion to be greatest there. Conversely, velocity slows on the inside meander of a bend, allowing deposition to happen there. And we see little sandbars that occur there. They're little crescent-shaped, elongated mounds of sand. And these are called point bars. So we would expect erosion on the outer part of a bend and deposition on the inner part of the bend. And that's actually how meanders get created and accentuated on a river system. Up to now, we've focused most of our attention on the erosive powers of river, which happen mostly at the headwaters, where the gradient is highest and where velocities are greatest. But that's only one of the two major roles that rivers perform. The second part is dispersing that sediment, and that happens at lower elevations with lower gradients. And when that river goes from a very confined high gradient area and then spreads out, it makes one of two depositional landforms. If it's in a continental setting where that river starts spreading out in an unconfined way, it creates an alluvial fan. And if that river dumps out into a marine environment or any sort of still body of water, like a big lake or an ocean, it forms a delta. Let's now look at what those look like. They're very similar, but alluvial fan is when that river system dumps out into a very broad, lower gradient continental setting. And it makes the form of kind of a fan, so it's a landlocked area. A delta, on the other hand, is when that river enters a standing body of water, either a large lake or a sea or bay or an ocean. It deposits sediment that goes underneath the ocean and forms what's called a delta. And the Mississippi Delta is one of the more famous ones. This concludes our discussion about erosion. And keep in mind, we have not covered the other two agents of erosion, which are ice and wind. And we've concentrated mostly on river erosion because it's the most dominant erosion by far of those three processes. So next time you're having a picnic on a serene riverbank and you look at the water, think about the hotbed of activity that's going on underneath the water. Think of all the erosion, the sediment, and deposition that's going on.